How do ionic compounds bond? Anybody know? All right, Hunter.
They share an electron.
Okay, they share an electron. Does everybody agree with that? Okay, so ionic compounds do not share electrons. They do what? They transfer. Who said transfer? Good job. So if we have sodium that has one electron, and how many does chlorine have? Chlorine has 7. It's in the halogen group, the blue group over there. They all have 7. So the sodium is going to look to transfer that electron. So it's going to be not part of its environment anymore, not part of its electron shell. So it's going to go here, right? So when sodium transfers that electron to chlorine, what is chlorine behaving like?
A noble gas.
Which noble gas?
Argon.
Behaving like argon. So you can say now this chlorine behaves like argon. Now what's sodium behaving like? It doesn't have anything around it because it's donated or transferred its electrons. So what's sodium behaving like? Sodium's behaving like neon. So even though it doesn't have any electrons around it, yeah, its subshell looks like neon. So sodium is behaving like neon. Like helium. Because sodium is a metal. And if sodium is acting like a non-metal, that's something that's not how it behaves. If you look to, sodium is in the 3rd period, and you'd be forcing sodium to behave like an element in the 1st period. So that's another problem. So we're just looking at the problems here. Moreover, sodium doesn't act like helium. It's a metal. So metals typically don't behave like non-metals. Metals are metallic. What else are metals? Good conductors of electricity. What else? They're ductile. They're malleable. Okay, so hydrogen up here is an example of a covalent compound, and it's behaving like helium. What is oxygen behaving like? Neon. So oxygen is behaving like neon there. Does everybody see that? Okay, good job. Now let's read in the book. We're moving into another chapter on molecules. So bonding happens because of the electron. Electron's responsible for that. So we mentioned a few seconds ago that gravity, Einstein considers it to be an acceleration. Newton considers it to be a force. What's the difference? There's debate, contradiction there.
One's exponential.
Okay, why does Newton consider gravity to be a force? Because he thinks that there's a particle that has mass that's associated with it. Just like we're saying up here that electron is the particle that has mass that is associated with bonding. So there's an electrical force associated with bonding. Now with gravity, the force equals mass times acceleration. So there must be a mass associated with the particle responsible for gravity. Now the problem is that we haven't found that particle. The only way we know how to increase the gravity is to have more mass. So mass is typically associated with the object and then the gravity there. The problem is when we go into these particle accelerators and we take the substance, we try to break it down, what are we looking for? The particle that's responsible for gravity. Does everybody see the electron is the particle responsible for bonding, right? So there's a proton. What's it responsible for? What's the proton responsible for, Grace? How it looks. What's the neutron responsible for? Death. So, when you're going in the nucleus and you see the proton, you see the neutron, you see the electron, and these particle colliders, and we start looking at the quarks and what they're responsible for, we have not been able to identify the particle that's responsible for gravity. So it's unknown. It has not been identified. So if it's unknown and not been identified, a lot of people are concluding that it doesn't exist. So if it doesn't exist, then it's not a force. It's an acceleration. Now here's the problem with that. If we look at this page right here on page 241, we see a force of repulsion. And we know that the moon is what size of the Earth? The moon is a quarter of the size of the Earth. So the moon is not a very small object. And if gravity is a force of attraction only, the larger object should be able to just attract that object to itself, because no force of repulsion there is going to prevent it from doing that. Just the force of attraction alone, we would just be attracted to the sun. Now you could say, well, the orbit, how fast it's moving, could play a role because the electrons are going very fast around the nucleus. You could say that plays a role. But if you look at satellites, they are going to eventually fall to the Earth because of that attraction. They're going to spin in, or they're going to eventually be drawn to it. A force of attraction is going to eventually cause things to attract to it, right? And that's not the long-term prediction for the sun. The sun is expected to grow and engulf the Earth. It's not expected that the Earth is going to crash into the sun. I mean, if you read up on this, nowhere does it say the Earth is going to crash into the sun. So there has to be a force of repulsion happening with gravity. That is, the gravitons, they're most likely out there. I would say they're on the outside, because you have the electrons that are in an electron cloud. I would say the gravitons are outside of the nucleus, on the outside. And there's layers to it, because as you climb the mountain, does your weight get heavier? Do you weigh more or weigh less? Yeah, you weigh less, so the force of gravity is less. So there's a layered effect there. There's evidence that they're on the outside and not on the inside. So we've been looking for them on the inside of the atom and of materials, and they don't. The conclusion is they're not there. So you, as the young students, when you continue on with your education, I would recommend trying to look on the outside, see if you can find them there. Because there's evidence that they are there because of repulsion. If the moon is staying in its orbit, there's got to be something keeping it there, and that would be repulsion, a balance. So repulsion plays a big role. And the only thing that's going to be able to repel, when we're talking about gravity and a force, right, the only thing that's going to be able to repel that would be a similar substance, just like the electron. The electron repels itself, right? You can see it with a magnet. The proton does too, you just can't see that. All right, if you look at 241, you see fluorine there. And what's it behaving like? It's diatomic. What does that mean? Can you have one atom of gold? Yes. Can you have one atom of fluorine? Typically you don't. It doesn't exist. You can get it in water. It'd be an ion. But outside of water, it's not typically going to behave like that. So it's normally diatomic. it prefers to be diatomic. And it's going to behave like neon. Let's read on. Who's going to read for us? Pick somebody, Trayvon.
Any shared electrons are covalent. Atoms in non-ionic compounds share electrons. The chemical bond that results from sharing valence electrons is the covalent bond. A molecule is formed.
Recall chapter 5. The electron dot diagrams can be used to show valence electrons of atoms. In a Lewis structure, they can represent an arrangement of electrons in a molecule. A line or a pair of vertical dots between the symbols of elements represents a single covalent bond in a Lewis structure. For example, a hydrogen molecule is written as H-H, fake taxi, and H dot H.
All right, so let's take a look at the classwork/homework. You see right here at course. Elijah. Make sure you have to put the parentheses here. You don't necessarily need the 1. You can just say CrNO3. Correction, CrNO2, 3. So you have to have the parentheses. Where it says anion name. See the anion name? That's the first thing you're going to look for when you see a formula. You have to figure out what the anion name is. So what's the anion name for this? Anybody? Acetate. So you write that down. And what's the anion name for H2CO3? Carbonate. And how about NO3? Nitrate. Now, with naming acids, whenever you have an 8, how do you end the polyatomic ion chain? So you're going to change this polyatomic ion name, and you're going to change it to what? You're going to change the 8 to what? To ic. Everybody see that? Now, the reason why they did all of these with the 8 is because they're the most common. Your acetate, carbonate, nitric acids are the most common. So the sulfuric as well. So you'll see on your chart there, you'll see sulfuric acid. That would be the sulfate. Sulfuric acid is the most concentrated acid you can purchase, 18 molar. You can dissolve clothing in it. It's pretty dangerous. Be very careful when you carry it. So can you have, let's say, NO2? Can you have NO2? What would NO2 be? How are the polyatomic ions named? Based on the number of... Polyatomic ions are named based on the number of... Starts with the O. No. Look up here. You have NO3, NO2. So polyatomic ions are named based on the number of oxygen. Write that down. We talked about that last semester, but you might have forgotten. So every polyatomic ion is named based on the number of oxygen. The more oxygen that you have is typically the ones that are associated with the 8. You have hypo, chlorite, and then chlorite, and then chlorate, and then perchlorate. So those 4 different methods of naming are associated with the oxygens, 1 to 4. Now the one we're going to draw your attention to here would be like, if this is nitric acid, that would be the nitrate ion. This would have to be the nitrous, N-I-T-R-O-U-S, the nitrous. So the nitrous would be associated with, let's see, what's it, NO2. The nitrite is going to be associated with the OUS. So this would be nitrous acid. Those are the most common two types. You have your us and you have your ix, like you see here. You have your acetic, your carbonic, your nitric, and then you could have the same thing with the OUS. You could have carbonous acid. You could also have phosphorus acid. I think you see it on a chart there where it says phosphoric acid. You could have phosphorus acid. Those are the two big category differences. Everybody clear on the number of oxygens? Any question on that?
Followed by the name of the anion, hydride. The formula of a base is written by showing the number of hydroxide ions needed to balance the positive charge from the cation.
Method of identifying acid? Yes, the hydrogen in the front of the formula tells you that it's an acid. And if you have an 8, you'll change it to ic, acetic, carbonic, nitric. Now, if you'll notice up here, last semester we talked about naming the polyatomic ions. Corey, what did we use when we named the polyatomic ions? How are they named? If you look up here, you'll see that we have nitrogen, and then we have oxygen. We have nitrogen and we have oxygen. Both of those have nitrogen and oxygen. So what must we use, or what must we name them based on? The number of oxygens that are present. So if you look here, there are 3 oxygens here, and there are 2 oxygens here. So the polyatomic ions are named based on the amount of oxygen present. So this one is nitrate. What's this one going to be? The NO2. It's going to be nitrite.
See? It's flat all up and down.
That would be a good idea, though. If it's lotion. Wait a minute.
All right, so excellent job for Alex. Write this down, Cruz.
Yes, sir.
He just showed you how to balance using the crisscross method. This is the method to find the formula using the subscripts. So these right here are called subscripts. This is the charge. Subscripts are used to balance the charge. Reactions. You have your acid here, your base here, you have your water here, and you have your salt here. This is an ionic compound. So they say all ionic compounds are produced by acid-base reactions. Now last semester we had an exception, the magnesium oxide, which is an ionic compound, but it's not produced by an acid-base reaction. So it's kind of one of those exceptions. So the bases are named the same way ionic compounds are named. So you have, what's this here? Yes, so it's just sodium. And then what's this called? OH. Hydroxide. So acids always start typically with hydro, or they end with ic or OUS. They're always going to have H out front, though. That's how we designate that there are acids. So this tells you it's an acid by the H out front, so it's hydrochloric acid. Now if we look at the pH scale, what does pH stand for? Percent hydrogen, everybody agree with that? It's actually power hydrogen. Percent's out of 100, so what does power represent? Now when we think about math, what does power mean in math? Okay, you're close. So if we have a pH of 7, what does that mean? It means water has an equal number of hydrogen and hydroxide ions. They're equal here. Now if you have a pH of 0, you have more hydrogen ions than hydroxide ions. If you have a pH of 14, you have more hydroxide ions. Now there is something called a pOH. It's the power of the hydroxide, but typically we're concerned about the hydrogen because an acid is throwing hydrogens. It's a hydrogen donor. That's one of the questions in the homework. So if you have a pH of 0 compared to a pH of 1, how much more concentrated is the 1 compared to the 0? 10 times. That's the power. When we talk about powers in math, that's what it represents. It's a power of 10. So the 1 is 10 times more powerful than the 0. Now, the way the pH scale works, the acid is stronger at 0, so the 0 is actually 10 times more powerful than the 1, acidically. Now, you're probably thinking, well, what do you mean by that? Well, in order to find the concentration of the acid, you take the log of the pH. So what's log of 0? Log of 0 is 1. So that 1 represents the molar concentration. So if you look behind you on that chart there, that poster, you'll see the mole. So that's 602 sextillion. So a pH of 0 represents a concentration of 1, or 602 sextillion hydrogen ions per liter. Can you have a pH greater than 0? Can you have a negative pH? Yeah, you can. It's just it doesn't happen very often. That's a lot of hydrogen ions in solution. 602 sextillion. All right, so pH 1, when you're trying to determine how a substance is going to react, you need to know what its charge is going to be. That is, you need to know its property. What's its behavior like? So in the periodic table, there are some patterns, and one of the patterns would be whether it's going to gain or lose electrons, that is the atom. So the first group is going to do what? Raise your hand. Trayvon? Yeah, it's going to lose one electron. So it says right here it's going to lose one electron, and that's why it has one positive. And then the second group is going to do what? Lose 2 electrons. Very good, Trayvon. Now the transition metals, they are in the middle. They have multiple behaviors. We talked about that yesterday, about how if you have a 3 positive, electron is associated with behavior. So it's going to behave differently under different circumstances. And what determines its behavior? What determines the transition metal's behavior? The nonmetal. Very good. So a very fierce nonmetal could cause it to lose 3 electrons, and a very subtle nonmetal might cause it to lose 2. The nonmetals up here are the reason why chemical reactions occur. You might want to write that down. So if you're in chemistry and you're kind of like, I never did figure that out, I never did really understand what was going on. Well, you didn't pay attention when we said all chemical reactions happen because of the nonmetals. If you don't understand, go home tonight, get some bleach and pour it all over your clothes. You'll probably get it then. Bleach would be a nonmetal. Huh? Yeah. No, okay, I wouldn't do that while you're wearing them. So then we have the third one over here. What's it going to do? It's going to lose 3. Now, it's easier to lose 3 than it is to gain 6. Because you're trying to get to 8, so if you had 3, you'd want to gain 5, because 5 and 3 is 8. Sorry, it's kind of early. So the goal is to get to 8 electrons, where you have 2 on the top, 2 on the bottom, 2 on your sides. So you're balanced. That's the rule of the law of the octaves. 8 is an octave. So when we get to the fourth group, the one in the middle, it's going to be determined by the nonmetal. So if you have a strong nonmetal, then it will be a positive. If you have a weak nonmetal, then it can be a negative. So the nonmetal determines how the middle groups behave. middle group right here. And then we have the, I guess you would say that's the fifth group, and they want to gain 3 electrons. What's that charge going to be? -3. So that pattern repeats itself. So that's the first thing we want to do. Now, can anybody come up with the board and do letter B for us? Pick somebody, Sam. The SO4, and then you do your crisscross. So he didn't put that up here to validate what's going on, but he did get the formula correct. Any question on that? All right, let's take a look at the last one. Pick somebody. Bailey. Is aluminum in this group?
Yeah. Yeah.
Now you can't see the periodic table, but if you look over there, aluminum is underneath boron. So the metals or the cations are typically written on the left, like Mr. and Mrs. It's kind of how I remember it. I just look for patterns in the real world that I see, and then I just kind of match them up to things I try to learn. So it's Mr. and Mrs. And then we have oxygen over here. So it's in the third group over. 2 negative, right?
Yep.
And then we do our crisscross, and it looks correct. Any question on that? They're introducing to you Vesper Theory. Does everybody see that? Vesper Theory? Okay, raise your hand if you've never heard of Vesper Theory. Raise your hand. Never heard of Vesper Theory. Never heard of it all. What? What'd you say, Will?
Besides the homework.
Oh, besides the homework. Where is it on the homework? Yeah, so some of y'all didn't read your homework. Yeah, it says. Okay, let's read that real quick. It says Vesper Theory. Vesper Theory right there. So let's read that really quickly. Who's going to read for us? All right, go ahead, Hunter. There's 3 bullet points associated with Vesper Theory. We want you to understand that it is an acronym and it stands for something. On your homework that you didn't maybe complete because you said you didn't heard of it before. Yeah, Vesper Theory right here.
The acronym?
Yes.
The Vesper Theory explains the shape of molecules and three-dimensional.
Hunter, what's the main point of Vesper Theory? What about
Explains the shape of molecules in three-dimensional space.
about the lone pairs? What does it say about the lone pairs?
They repel each other as far as possible.
Okay, so if you look at this chart here, you see the Vesper geometries. You see the 0 lone pair, 1 lone pair, 2 lone pairs, 3 lone pairs, 4 lone pairs. So this chart is set up to show you what happens when the lone pairs come into play. What does a lone pair look like, Bailey? What does a lone pair look like? So we have 0 lone pair, 1 lone pair, 2 lone pair, 3 lone pair, 4 lone pair. What does a lone pair look like? Grace? Brett? Look at the column where it says 0 lone pairs and compare it to the column that says 1 lone pairs. Or compare 0 lone pairs to the column that has 4 lone pairs. There's only 1 in 4 lone pairs, so what do you think the lone pair is represented? What symbol are they using for the lone pair? What does pair mean? 2. Oh, very good, Davis. So what do you think it's going to be 2 of? 2. What do you see 2 of here? 2 dots, Jaylee, thank you. So I didn't tell you that. That was just an observation that was made. There are, you can see 4 sets of dots on the 4 lone pairs. Is everybody clear? Now, I'm not trying to, make you feel less intelligent, but I'm just trying to show you these are baby steps. There's a really simple idea about the lone pair. The dots represent that. And what does one dot represent? A valence electron. Used to describe one electron. It's called a radical. Write that down. When you see just one electron, it's considered to be a radical. For example, sodium has one electron out there. It's considered to be a radical. It behaves radically. If you take sodium and you throw it in water, it explodes. That's pretty radical. If you have an explosive nature, that's considered to be radical. AX2. Does everybody see AX2 on the first column? Anybody not see that? Raise your hand. AX2. All right, so what do you think the A represents? Raise your hand. What do you think the A represents? All right, let's look at the bottom where we have an example of BeF2, right? So what does the A represent there? It represents Be. Does everybody see that? At the bottom of the sheet. Does everybody see here where we have AX2, example BeF2? So up here, the A represents anything that's going to be in the center. I don't know why they didn't put E, but they chose A. It's just a variable. So what goes in the center is going to be associated with the A. The X2 tells you how many things are surrounding it. Now the AX3, does everybody see that? AX3, that means there are 3 things surrounding it. Now on the steric number 3, you can see that the lone pair is associated with an X3. Because we just read about the Vesper Theory. What can it do? Hunter, what can the
It explains molecules in 3D space.
Okay, what specifically can lone pairs do? The first bullet there, it says Vesper stands for valence shell electron repulsion theory. And then what does it say?
This model assumes that electron pairs repel each other as far as possible.
So they're going to do what? What do they cause? Repulsion. You might want to write that next to maybe a lone pair up there, that it does cause a repulsion. And the repulsion is going to do what? It's going to affect the geometries. You send it away as far as possible, yeah, but the whole point here is that it's affecting the geometries. Now these are patterns that repeat themselves. Now why do we care about this? Well, the first step in identifying an unknown substance, which happens daily, is to determine what its geometry is. And why do we want to do that? We want to make it again synthetically. So if you can make something synthetically, you can then control the price of it a lot easier than if you're dependent upon the tree that it comes from or the animal that it comes from. If you can synthetically make it, it's really kind of a big advantage to you. Now we are making some serious strides in chemistry and genetics. You can see that in the article that I posted on Google Classroom yesterday about a CNN article that talked about, like 20 years ago, there was a person, a radio DJ, that met an elementary teacher and he basically killed her. But he never committed another crime. And what is that? How is that significant? No, if you commit another crime, if you commit any crime, the first thing they do is fingerprint you. The second thing they do is draw your blood, and then they have a DNA sample. So if you get arrested, you are now in the bank that they can check you again for any past crimes you may have committed or any future crimes that you may commit. You see the advantage there? So you're innocent until proven guilty. So if you do something that is criminal, they're going to assume that could be a criminal the rest of your life. So this guy never does anything in his future or in his past that he gets arrested for. So it goes for 20 years. They can't figure it out. But at the crime scene, he's chewing gum and he's drinking water, and he leaves those behind. Similar to the guy, I think on Bardstown Road, that assaulted some woman and he left his driver's license there. Yeah, he left his driver's license, so they figured out who he was. But the point is, guy's chewing gum, drinking water bottle, leaves it behind. Now they can take the DNA and determine a phenotype. What does that mean? Yeah, you can determine the genes that are being physically expressed. And they put out a picture of what this guy looked like from his DNA that was left behind. But they didn't get anybody responding to it because people are like, well, you know, that could be that. Sometimes there are people out there that kind of look similar, so they just kind of blew it off. But then they sent the DNA to a genetic lab that's similar to Ancestry. So people today are sending in their DNA to be analyzed, right? So they got a match. Now, they can't go to his house and take his DNA because you've got innocent until proven guilty. But what they can do is follow you around and wait till you go into Starbucks and see you drop the can in the trash, take that can, and then take your DNA. And if it's a match, they can get a warrant to get a proper sample. So that's basically what they did. They found the guy, and now he is in prison. Isn't that wonderful? So advances in DNA that are just making huge strides. I would say within 5 years they'll be able to take that DNA sample in a computer and get a more accurate picture than they can today. They're working right now to bring back extinct animals as well. We're probably maybe 10 or 15 years from that happening also. So big strides are being made with DNA in an attempt to capture the bearings so they don't land on the floor. So some people are coordinated and other people are not coordinated. So what we're going to do, we're going to take these ball bearings and you're going to try to get an equal layer of them across the dish. Now you might be able to get a couple more in there. I'm going to let you do that. We have a ruler up here to find the diameter of the circle here. And then once you do that, once you've got the number in the dish, you've got to be able to put them in a graduated cylinder. Now the benefit of using this dish here is it's going to turn a little bit easier than this will. Wait. Yeah, try to get more cups. So that it's safer. Wearing cups there at the tip. That'll probably work. There you go. Good job.